Good evening, everybody, and welcome to Astronomy on Tap Atlanta. I am your host, Dr. Justin Robinson, and it's my pleasure to introduce somebody who is very, very familiar with all of our outreach endeavors. Please give a round of applause for Dr. Slava Sadykov. Dr. Sadykov is a solar physicist, one of our solar astronomers in the department, who has a brigade of, I have lost count of undergraduates and graduate students who are doing significant research with him. And I've got nothing more to say. He's got a fun drinking game that he's going to explain to you. So if you don't have a beverage or if you're running low, please, we'll wait. Go get some more. And then after his talk, Jupiter is almost right above us, and we've got that thing that's going to make it look really, really pretty for you all. So please stick around after the talk. Without further ado, please give one more round of applause for Dr. Sadykov.
Thank you so much. Thank you, Justin, for intro, and thanks everyone for joining. Thank you. So I'm Slava, and as Justin explained, I'm either physicist or astronomer. So basically, it depends what you want to ask me. If you ask me an astronomy question, then I will tell you no, I'm physicist. I'm not going to respond. And same for physics, right? So if you ask me a question in physics, I will say no, I'm an astronomer. So basically, today we are going to talk about the sun, but in case if you are interested in activities, so you can select your level of difficulty, and we will be exploring three of those today, so easy, medium, and hard. Whenever this sign appears on the top right corner of the slide, or I'm pronouncing the corresponding words, so please take a sip or take a shot or whatever, so whatever amount you prefer. So in order to, proceed forward and in order to keep you energized. All right. First question to you folks. What is the closest star to the Earth? It is the sun. Excellent, excellent. Adults typically respond to this question worse with respect to kids, but you did a nice job. And the sun is indeed the case. So the sun is just something boring which is happening in our galaxy. So it is right there in the Orion arm. And if we zoom in actually a couple of times, we will find something like this. So this is our sun, and in principle, we did the zoom of 150 billion times from the scale of the galaxy to the scale how we would look like at the sun approximately. Very approximate, it is done in paint, so don't judge. But basically, it's like looking at the size of the human hair compared to the size of the Earth. So it is a very impressive zoom. But at the same time, the sun is something special for us, obviously. So on one hand, it's the ordinary star. So it's kind of in the middle of its lifetime through what we call the main sequence. So kind of an adult in their 40s, I would assume. But the thing is that it's closest to us and it is well resolved. So therefore, it's really the best. So first of all, it is the best plasma laboratory. So and those who selected the hard level, please take a sip. And it's also is very valid for us in terms of the cause and the source of life. So it is our primary energy resource that we have. At the same time, it might be a problem for us in the near future, given that how technologically advanced we are. And yeah, I'm claiming that the humanity is relatively technologically advanced. I know that not everyone will agree with that, but that's fine. So, and it's the best observed star ever, and it actually caused several Nobel Prizes as well. I would say it's obviously less fashionable with respect to the black hole and cosmology, but still it delivered many important scientific discoveries. And it's definitely more practical with respect to black holes and cosmology. Sorry for those who work in those fields. So, the sun is fascinating. This is actually how it looked like on May 9th, 2024. So on that day, we experienced one of the largest storms happening on the sun, which delivered aurora as south as in Georgia. The second event like this actually was in November of 2025. If you were lucky enough to observe the night sky on that day, you might have seen some faint flickerings related to aurora, possibly better to take a photo with long exposure. But yeah, so as south as in Georgia. And the sun is indeed fascinating. So this is extreme ultraviolet image of the sun. So the second question that we will try to answer is how we observe the sun. And we indeed do something like this, right? So we look at the telescopes, look for the telescopes, so what the astronomers are doing, and discover whatever physics is happening at the sun. But I have a question to you. How many times can you look through the telescope like this at the sun? One? Actually, two. Yes, you have two eyes, so you have two eyes to burn until you actually will no longer be able to interact with the sun anyhow. So obviously never look at the sun unless you have some filters in your telescope or unless you project it to the piece of paper by removing an ocular. So obviously, yeah, those are AI generated, so we didn't harm any astronomers by those images. And we use modern facilities to do that. So we use the remotely operating telescopes, and we don't put human beings in the primary mirror in order to avoid the sunburns. So, and this is the Daniel Inouye Solar Telescope. It is a 4.24 meter, the state-of-the-art facility that we have in Hawaii. And this telescope has two primary properties. First of all, it has fascinating images of the solar plasma, the word plasma. So, and this is an example of the very zoomed in image of the solar atmosphere. And just to give you the scales, right? So the scale of one granule here is about the size of Texas. So it's about 1,000 kilometers. This is what we call the solar granulation, effectively boiling of the solar plasma close to its surface happening. And in the same image, we see the beautiful sunspots, we see the structuring, we see the plasma outflows from the sunspots. So, and the second property of this telescope, as we will discover, it produces the vast amounts of the big data. So, it's really delivering a lot in terms of the data volumes with which we are dealing in astronomy. Another facility could be radio. So surprisingly, the radio astronomy of the sun is growing nowadays, and we observe the solar atmosphere throughout in different radio wavelengths. And we are borrowing some of the facilities with which astronomers are typically playing, so true night sky astronomers. So we borrow, for example, facilities like ALMA, and by tuning to specific wavelengths, we can scan through the solar atmosphere at different wavelengths and have not very high resolution, but still very important scientifically images of the sun. Another facility which we could potentially use to discover not the solar surface, but the very, very interior of the sun are the neutrino detectors. So, and this is just fascinating. So this detector that you see in the screen is called the Super Kamiokande detector. So we have various types of neutrino detectors. And the thing is that neutrinos are the only messengers which tell you what is happening right inside the sun. You cannot see through the solar surface because for photons it takes hundreds of millions of years to come towards your eyes. But neutrinos message that directly. They directly expose you to this nuclear reactor, which is right in the middle of the sun. And you can even reconstruct the images like this. This is the solar core, in some sense. And we obviously observe solar eclipses and question when did we observe the one last time here in the United States? 2024. 2024 and previously 2017. You will have to wait a long time until the next one on the US territory. I believe it's 2040, either 5 or 9, I forgot, unfortunately. So it will capture only the Montana and Washington, I believe, by its trajectory. So, but yeah, solar eclipses are fascinating. And this is the first time you are actually able to see what we call the solar corona. The sun is very bright, but if you dim it, either with the moon or with the piece of plastic, depends, then you can actually see the structuring around the sun, which corresponds to solar corona. And even those red brightenings, which are actually what we call the solar chromosphere. So this is kind of a transition region between the solar surface and the solar wind. What is interesting is that when I try to explore what this image is, it seems to be that this image caused a couple of inspirations. So first of all, yeah, the good ones, but unfortunately as well as bad ones. So this is exactly the same image, by the way, just a little bit processed. Okay. And we obviously launched a spacecraft. The word spacecraft appears, so we launched them to space. Why do we do that? Why do we spend billions of dollars to do that? Well, there are various reasons. First of all, the space doesn't have an atmosphere. It's actually good for observations because we can observe clearer. We are not dependent on the weather conditions. And second, because we can observe in the wavelengths in which we are not capable to observe on the Earth's surface. For example, ultraviolet. Our atmosphere absorbs it, fortunately for you, and for me as well. But in space, once you fly, you can see the sun in ultraviolet actually in many different channels. And you can see the structure of the solar corona. And I will show you a couple of more images later. What's tremendous is that this spacecraft is a geostationary orbit and actually delivers to us a lot of various signs. In addition to this, there are two more spacecraft which have launched just recently in 2017 and in 2020, which started to approach the sun closer to which we have ever achieved before. One of those spacecraft was Parker Solar Probe, and Parker Solar Probes observed the plasma of the solar wind at tremendous distances, at just 5% of the distance from the sun to the Earth, meaning that it experiences actually the heat, which is 400 times more than we experience here from the sun. This is why it actually mostly doesn't look at the sun directly. It's what we call measures the plasma in situ, meaning that it probes literally what the plasma is, what kind of elements does it have. And it also has imagers which are looking sideways and which are capable, for example, capturing the propagating coronal mass ejections, the plasma blobs flying away from the sun. And another spacecraft was Parker Solar Probe, and actually it is going to achieve its primary goal closer to 2029, closer to 2027, 2029, when it is going to have an angle of more than 30 degrees with respect to the ecliptic plane. The reason, and possibly the primary reason to launch it, was that because we cannot observe the solar poles from Earth, the solar poles are visible at very tiny angle of 7 degrees. But with the spacecraft, we'll be capable of looking into them at more than 30 degrees. And this will help us to understand how the sun functions as a star, how the dynamo processes are happening, and how actually plasma moves in that region. And yeah, we have a lot of data coming from the sun, a lot of big data, and many observatories in basically our possession in order to study from the sun all the way to Earth. So again, we have the deep space probes, we have the probes which are primarily near the Earth orbit or at L1 point. We also have the probes which are flying in our Earth's magnetosphere, something which I'm not touching too deeply in this topic, in this talk, because it's effectively a separate important topic and separate physics happening there. All right. Question is, why do we do all that? Meaning that it's understandable that the sun is fascinating, right? So it's cool. It delivers us very nice science. It's very important from the physical perspective. We discover a lot of interesting phenomena. But are there any other reasons why are we doing this and why are we spending the taxpayers' money for this exercise? Well, this is how the sun actually look today. So it was okay, I don't have the timestamp here, but it appears later. It was about 4 o'clock of the Eastern time. So it's basically about about 5 hours before. The sun didn't change too much since that time. So it appears to be relatively boring, right? So there are two sunspots on the northern side of the sun, and the sun is not very active, at least at the current moment. But those sunspots are manifestations of the primary reasons why we care about the sun from the operational standpoint. Those sunspots are manifestations of magnetic activity of the sun. The sun is a giant magnet, and sometimes it stores the energy in magnetic fields, releases those, and actually launches towards Earth. And it launches them in the form of the solar flares. What you can see here is the last strong solar flare of the previous solar cycle 24 in 2017. And we observe it in extreme ultraviolet. We see a strong brightening, which basically we refer to as a flare, and we see a lot of activity in the solar atmosphere related to that. We can see the solar plasma moving very nicely along the coronal loops. This flare actually caused a couple of unpleasant results on Earth related to energetic particles and coronal mass ejections. So, once you've launched the flare, you're actually going to potentially send a piece of the solar atmosphere towards Earth. What we can see here is a coronagraph, so it's basically an artificial eclipse. We shade the sun with the piece of plastic. What we can see then are those very nice outflows away from the solar atmosphere. And actually, we can see the moon as well. It does a very strange dance because this coronagraph is on the geostationary orbit, actually. So, but yes, we see the moon, we see the plasma outflows, and right when the moon is propagating, so the movie launches one more time, we can see right here a very strong plasma blob. It will appear right in a moment. Yep. So this is what we call a coronal mass ejection, meaning that a vast amount of plasma, which if launched towards us, could cause some harm. The sun is also magnetic in the perspective of years. We know possibly about the solar cycle that it lasts 11 years. What it actually means is that the sun accumulates its magnetic field first at the poles, at the solar minimum, and then via the mechanism which we call the solar differential rotation, it basically twists and transforms those magnetic fields to what we call the toroidal configuration, forms sunspots, and therefore favorable places for the flares to happen. And after some time, those magnetic fields again become rearranged to the polar magnetic fields mostly. And this cycle takes 11 years, and obviously it is well observed. This is, for example, the data series from 1960. So we quantified by the appearance of the sunspots, by the quantity which we call the sunspot numbers. And you can see this is what is happening effectively almost right now. So if we continue a little bit, we are somewhere here. So we are in the cycle which is slightly stronger than 11 years before, but still is not possibly as active as it was for 21, for the cycles 21 to 23. And we will discuss it a little bit more right in a moment. So I hope I convinced you that the sun is magnetically active, but what also has a magnetic field is our own planet. It's Earth. And Earth, if we go very, very close to the surface, is effectively just a giant magnet. It has a North Pole, it has a South Pole, nothing more like that. And the problem is that if you assume this giant magnet configuration on the global scale, you are making pretty dangerous assumption, comparable to you thinking that the Earth is flat, actually. So it's almost like the flat Earth perspective for the space weather physicist. So because Earth's magnetic field is actually becoming distorted by the plasma flying from the sun. What you can see here is obviously not to scale image of the sun and our Earth's magnetosphere. If I zoom in here, I still will see this ideal magnet configuration. But if I move further from our planet, I will start see some stretches of our magnetosphere. I will see the bow shock, I will see the magnetosphere which is brought by the solar wind to the right, And this is the interaction of the solar wind with our magnetosphere. And basically, what the sun does, it releases magnetic energy on its surface, and we talked about magnetic energy previously. It sends those magnetic field bubbles towards us. And the thing is that in space, if you send a plasma bubble, it moves together with its own magnetic field. Eventually, it reaches our magnetosphere and interacts with it. And if you interact in a certain way, you can release a lot of energy, you can accelerate particles, you can cause auroras. And this is what we call space weather. So effectively, the weather in space is how the sun interacts with our magnetosphere, how it, for example, causes the magnetic reconnection, how it accelerates particles, how it disturbs our ionosphere of our planet by the hard X-rays and soft X-rays coming from the solar flares causing ionization. So we call it space weather, and space weather affects many different areas of our life. So for the ordinary life, it possibly doesn't affect too much, although there are arguments that you could see it even in your energy bill from time to time, because the energy companies might get a small amount as an insurance against those phenomena. So, but on the more global scale, there are obviously power grids, which we will have to switch off or redistribute during the strongest solar storms. There are astronauts which are right in space, and although, according to the recent studies, the solar-genetic particle events are not causing the deaths of the astronauts, definitely no one wants to vomit in the spacesuit, right? So something which pretty nasty. So, meaning that it's a real hazard for us. And yeah, and in terms of what causes those hazards, again, we talked about solar flares, coronal mass ejections, and solar-genetic particles. Those are the fundamental elements of this. Okay, so just to return to the previous slide, I forgot to mention something. So one of the non-hazardous but very beautiful manifestations of the solar activity is actually the aurora phenomenon. And this is the sun as it was on November 11th, 2025. So on that day, we actually had the second chance in the recent couple of years to observe aurora in Georgia. So, and there are beautiful photos all around the globe, for example, in Mallorca in Spain, which is pretty south. So, all the aurora observations. And possibly this phenomenon did not really cause too much damage on our infrastructure, but we have some historical lessons. First of all, the term space weather is often referred to become more prominent at the time of 1859. So this was the first time when astronomers observed what we call the white light flare on the solar surface. Now we know that this event was very energetic, but there is another thing, actually, which had appeared approximately at the same time and became widespread: telegraphs, meaning that humanity started to become more intelligent, started to develop some fancy things, some fancy technology, and all of a sudden there was a connection. You observe something happening on the sun, and after some time, your telegraph lines stop working. After some time, yeah, there is some damage to a lines. There is some damage, yeah, to telegraph systems and aurora displays. So the dots started to become connected. Another phenomenon which happened in 1989 and caused very serious trouble in Quebec province in Canada was again the strong solar storm. And I really like the title of NASA for this day, the day when the sun brought darkness. So, and indeed, that's what had happened to the Quebec province, where basically the transformers and the power grids has been shut down for several days. You would possibly think that it is potentially not a big deal. Okay, so we have candles, we have flashlights, but think about think about people who rely on power very critically. Think about hospitals, think about first responders, etc., etc. So we, in principle, should not permit those things to happen. And yeah, the weather in space is important, and I would assume a group of very initiative space weather physicists had convinced the congressman that this is something to pay attention to. And we now have the ProSwift Act, which promotes the space weather research and operations and related mitigation actions. So I hope I convinced you that we care because we care. I mean, it's really something. Possibly it will not cause your death. Possibly it will not be a drastic change to your life. But for us, as for the humanity, this is something which becomes pretty important. And more important it becomes as we develop more advanced satellite systems, more advanced technologies. So as more and more we rely on the technologies. Okay, is the sun dangerous now? We already seen that, so possibly not, right? So we can see it in the white light, two relatively small spots. So we can see it in the magnetic fields on the solar surface. Yeah, there are some pretty interesting configurations, I would say, over here, but really nothing tremendous. And in ultraviolet, it is approximately the same story. And what turns out that it's really the case. So when we see the observations by the geostationary spacecraft by National Oceanic and Atmospheric Administration, and those are again pretty recent data, so possibly ended several hours before me being launched as a stock. So we can see that the sun did not produce anything very tremendous, although it seems that it has generated one M-class flare in the recent 24 hours, and those potentially could cause some interesting effects. The sun fortunately didn't launch towards us any energetic protons, so this has been quiet for the past 3 days, and to be honest, for the past 7 days at least. And in our attempts to predict the solar activity, this is what has been reflected. So this is the state-of-the-art predictions that we have at National Oceanic and Atmospheric Administration, the TXT file summarizing nicely the numbers. So very fancy. But without the jokes, so those are possibly the good statistical estimates that we can make on the sun. And we can see here that, well, yes, nothing in terms of the flare X plus flares, nothing in terms of protons. But for example, the M plus flare has been missed. It was only 10% probability for this phenomenon to happen. And it happened. But yeah, so basically it was not captured by the forecast. But what we really need to take a look is of more of the global perspective. So, oops, really? All right. It's very interesting. My apologies. I believe I lost a couple of slides when preparing. Okay, that's fine. So what I wanted to talk about is actually, although now the sun is not very dangerous, now is about time for it to become dangerous and about time for us to concentrate on its activity. Because what we have now is Artemis. Artemis is our second attempt to be on the surface of the moon since Apollo in 1968-1972. Yeah, you possibly know that Artemis is supposed to be launched during the previous weekend, but the launch has been postponed to March because of the hydrogen leak in one of the fuel tanks. So hopefully in March we will be witnessing the launch of Artemis 2. It will have 4 crew members. It will not land on the moon still, but it will make one loop around the moon, not a complete loop. But this will be the first time we are sending the humans that far since 1972. And the odds are that currently we are at the decline of the solar cycle 25. At the decline of the solar cycle 24, statistically approximately the same situation, we had the strongest event on the sun of the previous cycle. At the decline of the sun at around 1971, between two Apollo missions, we had an event which was possibly the strongest energetic particle event that we have observed throughout our history. So, in some sense, the Apollo astronauts were relatively lucky that they were not hit by that event. Again, most probably there wouldn't be any very strong damages to their health, but in any case, we want to avoid any unpleasant situations. What I want to emphasize is that even though the sun is not very active now, it might deliver to us some surprises. And we try to study the sun, but the problem is it's a lot. I mean, it's a lot in terms of dimensions, it's a lot in terms of various observations that we have, and the human brain is not designed for that, unfortunately. But machines do. And I would like to introduce you to the topic of machine learning, which we apply pretty actively to the solar study. So you possibly experienced machine learning a lot of times. So I'm sure that nowadays you interacted with ChatGPT, Gemini, and some other fancy tools which write the text for you, sometimes do simple tasks. So, and you know well that it is better to formulate your questions very precisely. So this is exactly what we are doing in our science. We are trying to formulate questions as detailed as possible. And regarding machine learning, yeah, I found that cartoon very interesting, and we will return to it at the end of the talk. So, machine learning is one of our technological advances, and in principle, it also depends on the external solar activity. And this is the cycle of AI life, as it was proposed in one of the Reddit threads. So, but another precursor to application of those very intensive computations to solar physics are the amounts of data. We really have big data now. For example, the Solar Dynamics Observatory is accumulating around 10 petabytes of data. An ordinary laptop is 1 terabyte, about 10,000 times less amount of information. Then you know a solar telescope will be close to 40 petabytes in its prime. And we are just starting. I mean, indeed, we are not going to stop with our technologies. This amount of data is again impossible to be browsed by the human being. We do machine learning. How do we do that? Well, it is a very simple example. So just to illustrate, suppose you are a solar observer, and suppose you mentioned the number of the spots on the sun. So I'm looking at the sun, not through the telescope, but project to the paper, remember, right? So, and I'm counting the number of spots. So I'm making an estimate of how active the sun is. And I'm also looking at how many flares it produced yesterday. You know what is the best weather forecast, right? Same as yesterday. Always works, almost always. So, and the same with the sun. So basically, those are those two parameters I observed historically, and I painted my points into red or green. So basically, whether the flare had happened today or didn't. So something like this I will get. And if we look closer, well, suppose next day you do those two observations, and your task is now to actually predict, to actually make a decision whether you are expecting the flare or not expecting the flare today. Based on the historic data, you can possibly very approximately build a divider between green and red dots. Yeah, there are going to be mistakes. So most probably those are not going to be detrimental. So somewhere in the decision boundary, not very powerful. But now you make a decision about this point. Okay, it is on the left side from this divider, so no, there is not going to be the flare today. This is pretty much what the supervised machine learning approach is about, the classification approach. So it is about looking at the history, making sure how you build this division between points in this multi-parameter space, and therefore every new point that you have, you can classify. And we do pretty much the same with the sun, with the exception that we really have a lot of different dimensions here. I presented you just a two-dimensional plot, right? It's relatively easy to percept. Three-dimensional plot, well, it's a bit heavier, so we potentially want to rotate it, to twist it in order to explore a little bit more. Four-dimensional, I mean, I don't know, I cannot visualize tesseract or something like this. So four-dimensional is out of my perception abilities. So right, so and with the sun we have a lot of dimensions. We look into the strength of the solar flare. We look into the speed of this plasma bubble that will launch from the solar surface. We look into whether these events had happened before, and whether there are any seed particles sitting in the solar corona and waiting to be accelerated. So there are many factors that can, in principle, adapt to something serious. And obviously, we are not doing that from the statistical perspective. Potentially, we would like to employ some machine learning algorithms. We quantify the sun in terms of those properties. We, based on the history and by applying certain algorithms, we are trying to learn. And then, once the new point appears, we are trying to make our predictions. So one of the key challenges here is, unfortunately, as with many dangerous phenomena on Earth, that the solar flares are pretty rare. I mean, to have really strong event is possibly 1 in 10 years or something like this. To have moderately strong, well, once a year. And this presents a challenge. Again, if we look at, for example, 100 mega electron volt particles exceeding a certain threshold, so something which makes sense operationally, actually for missions like Artemis, so it's about 1 to 150 odds of getting this. What's the problem? The problem is that if you always answer that nothing is going to happen, you will be 99% accurate, okay? So if I develop a test for flu, for example, which is going to predict that nothing is happening to you and ask all you to test that test, I will get 99% of accuracy, even though some of you might have the flu like starting to be developed. I hope not, obviously, but still. So the problem is that we need to pay more attention to those very rare events in our data set. And also, unfortunately, this rarity impacts how, first of all, it impacts whether we can transfer our learning beyond the period of time on which we have acquired our knowledge. So, as an example of one of the papers that we have published with students, we tried to learn whether we could use the most modern observations of the sun, the period during which we have the most advanced observations. And it seems that we actually cannot. So statistically, this period was different with respect to what we have observed previously, which delivers a lot of false alarms, meaning that our algorithm always constantly screams that something is going to happen. And you know what follows, right? If you constantly scream and nothing happens, when something really happens, no one is going to respond. So it's dangerous. It's pretty. It was a pretty interesting exercise. We also try to explore, for example, again, how the volumes of observations can impact your decision. How much data you need, how many dimensions of data you have to consider in order to build your forecast. And this is one work as an example. We are actually also trying to teach AI to make, not only to make the blind decisions, but also to explain to us a little bit what is going on. As an example, so if there is a decision which could crucially affect your life, hopefully in a good way, would you trust a completely blind algorithm telling you that you need to follow that? You need, for example, to do this or to do that without any explanation? Possibly not, right? Possibly you would like to hear something about the reasoning. Okay, you're telling me, for example, that I need to do that action. Why? And this is what we are trying to also learn from AI. AI doesn't give it for free. We need to adjust our algorithms. We need to implement the certain learning methods to do that. Okay, so, and related to AI, just, yeah, a bit of slide here. So, in AI, we recently have the boom of transformers, so based on which basically all the large language models have been built. And yeah, and basically we are feeling now that we are having three types of transformers. So those that don't care about space weather, those that actually suffer from this due to, yeah, due to coronal mass ejections, and those that help to predict. Okay, that was a bit off topic, but that's okay. Okay. Now, what else can we do? Well, given the rarity of those events, we can actually build the inference about those events from our knowledge of physics. We can simulate those. Physics simulations don't care whether the event is rare or not. They simulate whatever you want to. And indeed, this is also something which we try to do with the sun. We simulate the sun on supercomputers. For example, we do the simulations of the coronal plasma. That's one of the simulations that I have done previously of the solar corona and some visualizations, very detailed one. And very interestingly, in addition to modeling the solar phenomena, we now also start digitizing the sun. We literally start developing something like ChatGPT for the sun. And was very recent, and some of the GSU colleagues, not me, but some of my colleagues, were involved directly in this. So you developed what you call the foundational model, something which does not make any sense by itself, right? Like ChatGPT. It doesn't serve any particular purpose. But when you start asking it specific questions, it starts giving you specific answers. And there are many attempts to fine tune ChatGPT like algorithms, LLMs, to, for example, do the better coding, generating images, or anything like this. So the foundational model for the sun is something like that. By itself, it does not give you any answers, but with very little effort, you can fine tune it to flare prediction, recognition of active regions, for example, prediction of the solar wind, or some other interesting exercises, what we call downstream applications. Something in which I'm involved in is related to large amounts of data with respect to the simulations of the coronal mass ejections. We have about 30 terabytes and correspondingly about 23,000 different scenarios of coronal mass ejections propagating from the sun. And what I'm trying to understand personally is what kind of physical inferences with respect to, let's say, the magnetic field with which CME hits Earth, we can learn from the simulations in order to apply these for our observations of the sun. So, for example, we can see that only very straight pointing coronal mass ejections can deliver a strong negative BZ magnetic field, which typically drives very strong solar storms. And that coronal mass ejection typically has to be relatively wide. I will confess I'm still investigating the parameter space here because those facts are relatively well known, but by digging into the parameter space and by digging into different scenarios in simulations, we will try to enhance our physical understanding of basically the real life scenarios coming from the sun. And the very last topic that I wanted to possibly address today is related to the data itself. So, how to prepare your data? And, well, it is possibly complicated. So, let us consider something simpler, okay? How to enjoy your drink? What should you do? Well, there are two different paths. One path, you mash grains and extract sugars, then you boil the wort and add hops, then you cool the wort, add yeast, and let it ferment. After this, you pour this drink into your glass, so you enjoy it and hopefully you stay alive after, right? Which is the most important part of it. You see, there are many, the process is long and there are caveats. You might do certain things not correctly. So, but you can trust the local brewery instead. It's made for you. Just pour into the glass or even ask them to pour into your glass and enjoy the drink. And yeah, it's not the advertisement of the event here, don't worry. So it's just for you to understand that we can prepare the data and serve the data itself. And at Georgia State University, we are doing this. We have several data sets for which we spend a lot of time to basically prepare them for the particular purpose, such as flare forecasting, or the one with which I'm more densely involved is related to the aviation radiation. So, and again, there is a lot of data preparation and a lot of domain knowledge which goes into those data sets. And someone who just would like to test their well-advanced AI algorithm can directly work with those instead of going along the very long route of preparing the data. Okay, so kind of conclusions here. So the sun is obviously not something stable. So we know well that it is effectively a thermonuclear bomb, which speeds from time to time plasma towards us. So that's fine. And we possibly cannot do anything with this so far. But what we can do, we can mitigate, right? Meaning that whenever the sun, for example, emits energetic particles, possibly it's not the best time for astronauts to do EVAs. When the sun sends a coronal mass ejection, possibly it is a good time to disconnect long power lines and just wait for some time. When the sun emits a strong solar flare, possibly it's good to notify your neighbor across Arctic region that you will lose the communication soon. So it's pretty sensitive. And yeah, and correspondingly, it's possibly good to know when those are even happening because you possibly want to enjoy aurora. And yeah, for the points above, the prediction, the space weather prediction is very, very important. And as an alternative conclusion here, I would like to emphasize that possibly and hopefully this is not the scenario that we are going to witness with respect to AI, but I really want something like this, that AI and human beings realize that space weather is something which affects both sides, become friends, and bright future awaits, I would assume. With this, I would like to thank you so much for joining today and waiting for any questions you have. Thank you.
Thank you so much. Just one quick note before we take questions for Dr. Sadykov. Astronomy on Tap Atlanta has been an entirely free program to you for over 2 years at this point, and it will continue to be a free program. But I will say, besides when we have privilege of serving a faculty member to you, most of the time the presentations are done by graduate students. And so if you want to directly support their publications, their travel to research conferences, their cost for applying to jobs after they finish grad school, whatever you're willing. If not, please just buy a beer. We will take questions. I'm going to steal the first question for you if you don't mind.
Of course.
Could you go back to your simulation of the solar aurora?
I don't have ones, but
Or the corona, excuse me, the corona.
Corona. Okay, it's clearer now. Let's go.
Yes, okay.
Yep.
So there have been many folks that have lamented that they didn't post a video to YouTube about 10 to 15 years ago of just a recording of a fireplace, because those have gotten millions and millions of views and have made so much money based off of YouTube advertisements. So, do you have any plan to post this to YouTube and call it a fireplace?
Yeah, this is actually, I discovered before Christmas that HBO, I believe, has multiple fireplaces as a default instances right before Christmas. That's a perfect idea. I would like to have that one. Yep, sure.
Any other questions?
I will not get any money for this, so it will be free.
All right, we got one right behind
Sure.
Hi, I have a lot of questions, but I will ask just one for right now. So when you're actually like training your model or with your data set, do you guys use like local AI, like on like any NVIDIA GPU, like Obama or DeepSeek's 10 billion parameter model to use like RAG to train your stuff? Or do you guys strictly do this by machine learning programs on like scikit-learn and things like that?
Yep. Thanks. Yeah, that's a great question, and I believe it's very much depends on what exactly you want to do. So, in many cases, our problems are not very, I would say, intense computationally. So the data amounts with which we are dealing after all this processing are tremendously reduced. But there are some other problems like class imbalances, for example. And in this case, even the local setup of the machine learning, for example, scikit-learn in your own laptop works just perfectly. For the stuff like this, Syria, so I know that it's far not every GPU will support, which will support it. So meaning that I don't remember how many parameters exactly they have here, but given that they fit 4K by 4K images into this model, I would assume it's very, very heavy. So meaning that for this type of a model, you definitely have to have that one stack. And in my opinion, it is important to develop both. So there is a lot which we learn from relatively small and confined machine learning experiments, from, for example, experimenting with the class imbalance treatments. And there is a lot that we are advancing by bringing the cutting edge computational technologies here, such as GPUs, such as very high resolution data. I know that there are some people who are utilizing LLMs, for example, so trying to stitch the LLM with the particular goal, say prediction of the solar flares or so. So yeah, I would say it is a lot to explore here, and the most importantly, every attempt is valuable. Every attempt can teach you something new. So in my opinion, both are very important to do. Thank you.
Oh, I'm sorry.
Yep. Oops.
So earlier I saw saw the diagram that had like the cyclical layers and like how many sunspots there were
Yep.
every like 11 years.
Uh-huh.
What causes the variation in how many? Or why is it so
Uh, okay. Okay. If that wouldn't be recorded for YouTube, I would make one joke, but I will not, unfortunately. I'm really ashamed in front of my colleagues who do the prediction of those experiments. But so far, so let me scroll to this diagram just to emphasize the context. I would say so far there is no good understanding how to basically predict the solar cycle. Okay, so we know that there is a connection between the solar polar fields and the solar minimum. Uh, okay, sorry, I believe, yeah, I have to scroll all the way to the, oh, yeah, here we go. Okay, what we know is that there is a connection of the solar polar fields at the solar minimum and the next maximum. A problem, and there has to be a physical connection. This is the field that you effectively start working with when developing the sunspots, when developing the solar activity. The problem is that from the statistical standpoint, we have only how many, 4 or 5 points, right? So, and you can obviously draw the straight line, but possibly it's not going to be the most accurate given uncertainties. So we don't have enough statistics. So I would say in 100 more years, I will answer your question precisely. But so far, unfortunately, we don't know exactly what causes that. So, and how to predict more accurately the strength of the next solar cycle. I know that there are many modeling efforts with respect to the dynamo simulations of the sun going on, but yeah, so far I'm not aware of any very conclusive results here. Thank you. Yeah.
Regarding the Transformers,
Yep.
I do not care about space weather. You should put that on a shirt and sell that. That's my first point. The second one was for the Carrington event, which you touched on briefly.
Yes.
What would be, they had telegrams at the time, what would be the modern day equivalent? If that happened tomorrow, what would be, I guess, the effect on our modern day society?
Excellent question. So hopefully it's not gonna happen tomorrow, but so yes. Yeah, I would say the power lines. So you definitely have to disconnect very long power lines to basically avoid driving currents through them. So the voltage difference is defined by basically the distance along the power line, and longer they are, like larger the voltage difference you can drive through. And yeah, I mean, if you wouldn't disconnect those, you possibly will lose power pretty much in the northern regions of the United States and in Canada. If you would disconnect those, most likely this effect will be mitigated. But then you need to look into other aspects. You need to look, for example, if it is a strong flare, what it affects the ionosphere, a layer of the solar atmosphere, which we actually use for communication using radio waves. And when we have strong solar flare, or say strong flux of energetic particles, it affects ionosphere, it increases the density of it increases the ionization degree. And then you affect how your radio waves are propagating or reflecting. Correspondingly, you are losing communication, and I would assume the stronger the event is, the larger is the area around the polar cap where you are losing communication. So communication might be lost for some time. Then you possibly, if you are living a little bit in future, you might not have your food delivery on time as well. So because if it is done by the autonomous drones, then your GPS GNSS systems, which are using triangulation, may also mess up a little bit with respect to the positioning of this drone. So basically, triangulation is the basic mechanism for that. But whenever we disturb the ionosphere, we disturb the speed with which the satellite communicates with us. We disturb the refraction index. And therefore, we calculate the distances not that correctly. It still would be about half a kilometer accurate, according to recent events, but yeah, it might be pretty off. And lastly, unfortunately, I don't know exactly what might happen to the spacecraft equipment, meaning that whether you would have a lot of, say, single upset events in the spacecraft electronics, whether you, to what extent your equipment is going to be damaged. I would assume, again, if you turn off the spacecraft, not too many things might gonna happen there. So it definitely would be bad if you have that event and when human beings are on the way to Mars, for example, which, I mean, yeah, it's where it becomes sensitive. Yeah, I'm not sure if I responded to a question. It's actually great, but yeah, it's just my, I would say, estimates with that respect.
Right. You have a way rosier picture of the future of humanity than I do. Let's do one last question before we start doing observations of Jupiter.
I think it was on maybe the very next slide or near here. I'm trying to understand why do auroras, or maybe the next one, why do auroras only happen in the northern regions? It looks like that's one. The incoming solar particles, it looks like they kind of slip in a little crook there. Is that right?
Exactly. Thank you. This is the excellent question, and let me comment on this. So basically, aurorae are phenomena which are caused by energetic electrons which precipitate into the Earth's atmosphere and are interacting with oxygen, nitrogen, so with the elements which we have in the atmosphere. The thing is that those particles are charged and they really don't want to move across the magnetic field lines. So what you can see here are the magnetic field lines very approximately, and electron can move along very nicely. So it doesn't have to be very energetic to move along, but it has to be really extremely energetic, which doesn't happen a lot, to move across. So correspondingly, whenever you have the influx of particles, this is their preferred direction. They just move along the magnetic field lines, and you see that most of the field lines are ending at the polar cap. So this is basically the easiest place where the electrons can access our atmosphere. And this is why you observe aurora exactly in those regions, because it takes them much less effort and from physics standpoint, much less energy to access this portion of our atmosphere. Whenever you have, for example, strong shakings of this magnetosphere, for example, you shake this image a little bit, your magnetic lines start to wobble, so meaning that electrons can access a little bit deeper region first, and second, also there might be more electrons, there might be other interactions which are causing electrons at lower latitudes. So therefore, if you very strongly shake this system, you might potentially have the electrons falling down in the mid latitudes, for example, over here. So, but it takes a lot of effort of the sun to do that for you. So yeah, I would say aurora actually are relatively common phenomena, meaning that during the solar maximum, they occur very frequently if you are living very north. So, but in order to observe in Georgia, obviously, yeah, it takes a lot of time to have one. Thank you.
All right. Thank you, everybody, so much. We'll be sticking around for questions. Thank you. Yeah, please give them a round of applause.
Thank you so much. Thank you.
If ever anybody wants to know when Astronomy on Tap Atlanta is doing anything ever, pause for dramatic effect.
I have no idea
One
what was
more time.
that.
I saw it. We have some QR codes for you to our social media page. Amazing. Look at that. Okay.
Thank you so much.
If you want to know when we will be, where we'll be, what time we'll be, scan this QR code. If you're on a laptop, scan this QR code. And if you would like to support us, scan that QR code. If you give me just a couple of minutes, I'm going to get Jupiter into the lens of that. Thank you so much again, everybody.
Thank you so much for joining. Thank you.